Hi, this is Dr. Stephen Jones. We're going to be looking at programming applications with NLP in Chapter 8. And the reason we're doing this is we looked at how to do linear programming and what ideas were behind what it could do for you and pitfalls that you might have, and how to use Excel Solver to be able to solve these kinds of problems. And so we're going to do the same thing here, but look at specific applications within a business framework that you might use linear programming for, and then how to solve these with Excel Solver. And again, if you haven't downloaded the add-in, download the add-in. Okay, so let's suppose you were looking at a gambling club and they were looking at trying to maximize the audience that they could reach in their marketing campaign, and there's a constraint of a certain amount of money that they can spend on advertising, and not all of the advertising media will get the same amount of reach out there, and so there's going to be constraints for that. In this situation, they need to have, remember, going back to this part, $8,000 is their budget, but they also have to have at least 5 radio spots, and they can't spend any more than $1,800 on radio. So radio would reach out to a fair number of people. It would be relatively inexpensive compared to the others, but if they spent all their money on radio, then they wouldn't spend any on newspapers or TVs, TV spots. So they have to try to reach as many audience, as a larger audience as possible within the $8,000 budget that they have, and within the constraints of needing to spend at least a certain amount on radio spots, because that's one of the other constraints. Now, you can see this within the text or looking at the PowerPoints on your own, so I'm not going to spend a lot of time here. I'm not going to read each of these constraints, but you'll notice that each one of those has a certain number of spots that can be bought, with your objective being how many audience members can you reach. It's not a profit one, it's size of your audience that you're going to get to with this marketing, and then limitations in terms of which media you can use a certain amount, and costs, etc., that go into this. So if you put all of these into Excel Solver, and then highlight, if you've looked at my video about how to highlight and create those constraints within Excel, then this sheet right here helps you to understand, once you've powered through Excel Solver and highlighted the data and the constraints in there, then what you come out is this solution right here, where your maximization of audience is a little over 67,000 people being reached. I know finding 0.3017 of a person does not sound appealing, but we would either round it down to 67,240 or round it up to 67,241, depending upon how you wanted to round. But this is the more exact numbers, just in the same way that no television station's going to allow you to buy 1.9688 of a spot. You'd have to buy 2 spots. You could buy 5 newspaper spots, or you'd have to round this down to 1. Now, here's the thing. Because you can't buy that exact number, you would actually have to play around with this. So this number right here is what Excel Solver comes up with. If you could cut this like 0.9688 of a pound, you can do, likely. You know, if you had that much water, you could come up with that if you had something that could measure that specifically. But when you have to buy in lots, when you have to buy 1 or 2 or 3 or 4 or 5 of something, then you're going to have to see what impact rounding this up to 2 and rounding that down to 6 would have on the actual total audience right here. So this gives you an idea of what the decision is, what the best option is, and then once you get to the realistic numbers, you have to determine, okay, have I overspent my budget or underspent my budget, etc. Well, there's a manufacturing application, also a production mix. And again, we looked at tables and chairs before. There's lots of other ways to do manufacturing applications out there. And you could take a look at such things as what's going to be the lowest cost for you, how can you stay within labor or material requirements, are there product demands that create a problem for you? So you're looking for the best solution possible, and perhaps labor planning is one of those. Maybe you've got a certain number of employees, and in this case we're looking at the Hong Kong Bank, where they have full-time and part-time tellers, and they need to be able to make sure they can cover all the stations, but they have certain kinds of limitations, such as people like to go to lunch, and some people don't want to work full-time. And there are probably cost constraints that go in with this, and time constraints. Do you need everybody throughout the day? Do you need as many tellers in the morning as you need in the afternoon? And so once you get constraints like these that are within this problem here, then you're better able to do a scheduling. And that's what this linear programming problem is all about, is scheduling these people. So if you have this constraint, part-time workers must put in exactly 4 hours per day, can start anytime between 9 and 1. They're inexpensive, so they earn 8 hours a day on average. So if a part-time worker comes in, you must have them work 4 hours. Full-time workers work from 9 to 3 and have an hour for lunch. So you don't have to worry about the number of hours they have. They're going to work 9 to 3. They've got an hour for lunch that goes in there. You need to figure out where the part-time workers are going to be and how many full-time workers you're going to have. And then part-time hours are limited to a maximum of 50% of the day's total requirements. So you can't use only part-time workers and no full-time workers. You can only spend as much as 50% of your labor hours for the day as part-time. So if you were to look at those actual requirements out there, you would start saying, okay, when do I need to put certain people in, and should I have more full-time during some part during all day, or should I have more part-time in the morning? How many need to go in there, etc. This is a set of constraints, because what it says is you need to have 10 people on, whether they're full-time or part-time, 10 people on duty from 9 to 10. Certain number from 10 to 11, 11 to noon, noon to 1, blah, 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 blah. So these constraints out here tell you the number of people on duty during time periods out there, and those are constraints just like anything else. So you don't need to have full-time tellers starting at 9, 10, 11, 12, 1, because only part-timers can start at 9, 10, 11, 12, or 1 o'clock. Full-timers work the entire day, less the lunch hour. And you need to minimize the cost of labor here, and the cost as you see at the bottom, $100 for a full-time person, and then $32. That's because a part-time worker costs you $8 an hour, and they have to work exactly 4 hours. So they're $32 times how many ever start at 9 or 10 or 11 or noon or 1. So when you put that into perspective within your table, this is what your equations look like. And your Excel solver would, obviously without this information or that information, would be in there. This is the set of constraints and your costs, left-hand side and right-hand side. You toss this into Excel solver and it comes up with 10 full-time people start the day. No part-timers start until 10 o'clock. 7 start at 10, 2 more start at 11, 5 start at noon, and no more start at 1. And then, 4 hours later, these people get off. 4 hours later, these people get off, and these help to close. And so your full-timers, 10 full-timers are there throughout the day. Your total cost minimized is $14.48, and you have here got at least 10 people on. You'll notice that you have extra people on at 10 o'clock. You got 17 instead of just 12, but remember that constraint was you need to have at least 12 people on, not necessarily exactly. So right here you'll see the number of people that are on, number of hours that are on the shift, and how many are going to be calculated all the way through. Let's suppose you want to do a financial application. You're trying to do the best you can to create perhaps a portfolio that makes as much money as possible or gets the highest overall interest rate out there. So you can maximize any kind of returns out there that you want to. And again, it could be dollars or percentage or number of customers, whatever that's going to be. So in this situation, let's take a look at this example right here, International City Trust. And they invest in different kinds of investment opportunities. Notice trade credits, bonds, stocks, and loans. And there's only so much that can be put into any one of these areas because they want to diversify their holding. If it was all in gold and then gold tanked, then there'd be a problem. So bankers and other investors typically will diversify into multiple kinds of investment opportunities because it provides them with a reasonably good return and a fair amount of risk reduction. Even if they are risk takers, they still are not typically going to be illogical about it. And most bankers are not totally risk averse because it's risky to get into business in any case. So how risky they are will show up in the kinds of investment vehicles that they're willing to look at. So you see in this table the amount of interest that is earned by each one of those investment vehicles and how much they will let you put into any one of them. So it's a minimization. Well, not minimization in this case. You're trying to maximize the return. That's your objective. But you've got to be an equal to or less than the investment there on the right side. So now you're told ICT has $5 million to invest. So that's the limitation in terms of the entire cash balance that can be put into those 4 areas. They want to maximize the return, and they want to have enough diversification across the 4 vehicles to limit the risk problems out there. At least 55% of the funds have to go into gold and 15% into trade credit, and those are your other two constraints. So we start looking at what our constraints are going to be if we were to write them out, and that's what it's going to look like there, where you need to have less than or equal to $1 million in the first, $2.5 million in the second, $1.5 million in the third, $1.8 million in the fourth, and then the third and the fourth have to be at least 55%, at least 15% into the first vehicle. All of them together can't have more than $5 million in total, and then each one of them has to be 0 or more. Again, you can't have a negative amount, so you can't have a negative $1 million invested in gold or stocks or whatever like that. So the solution that you get with Excel Solver here when you put it through says that you're going to have $750,000 invested in the bonds, $950,000 in gold, $1.5 million in construction loans, and $750 in trade, $950 in bonds, $1.5 in gold, and $1.8 in construction, and you will get a maximum total return of $712,000. That's your guesstimate that you would get. It's not a guarantee by any means when you're out in the market, but it meets all the constraints that you're looking for. And again, you're using these cells within Excel and Solver to create the proper amount of investments for the constraints that are given by the company. Then you've got what can you do with the truckload. This is the truckloading problem is one where you're trying to maximize amount of profit or amount of goods that are being shipped, or miles that something can be driven. And in this case, we're going to take a look at a company named Goodman Shipping, and they are going to try to maximize the value of the things that are going to be loaded onto the vehicle, so that they can maximize the amount of money that they're going to make off of it. There are limitations that states will allow you to put weight into trucks. They can't just load it all up. There would be vehicle limitations out there as well, and some things are more valuable than others. So you could get something relatively heavy, such as paper, that takes up a lot of room and has a lot of weight, but doesn't have as much value, whereas you could also put gold in there in the same weight. It's going to take up less room. It'll weigh the same amount, but it'll take up less room. So you could theoretically put a lot more gold into the same space that paper would go into, but then it would weigh a whole lot, and it'd be a whole lot, have a whole lot of value, but it might create other kinds of problems like crime, etc. Okay, so a truck loading problem, you're going to have different sets of constraints on than we were looking at with a finance problem. So in this case, Goodman wants to maximize the value of the stuff that's put into the truck. They can't put any more than 10,000 pounds of stuff into the truck, and we're looking at proportions now instead of just specifically items, and so we'd like a proportion of the weight that's in them. Okay, so you had, if we go back, the first one, the value of each item, a certain amount, value for those items, and the amount of pounds that those items are going to weigh. You want to maximize the value that goes in here, so the number of each of these items that's in there, but you have to have a certain amount of weight for each one of those as well, and there's a maximum of 10,000 pounds of capacity, and you can't have more than one of any one of those things. There's just one of them. So they're trying to get as much value in there, but they got just one of each of these items. So we're not looking at 15 items or whatever. You just got a bar of gold or a whatever it is. You can still throw this same thing into Excel Solver, put it into a spreadsheet, and then use Solver to calculate it out. And what it comes out is that you would have a third of whatever number 1 is, and 1 full of number 2, and then leave 3, 4, 5, and 6 off the manifest completely. You wouldn't use it whatsoever. And you'd make yourself then $31,500. Now, if you can't cut up number 1 into thirds, then you'd have to go back and consider whether or not you might make some other use of it, of that same weight allowance out there. So if you have units that can't be divided into smaller pieces, then you would reduce the value of that load, go back, and the amount of money that you would make would be $24,000 instead of 1/3 of $22,500, which is $7,500. So what it's saying here is that you'd make $24,000 instead of $7,500, and you can't round things up. You might have to round things down if you can't take percentages of goods. And so it might cause you to make a different decision, but linear programming would have gotten you to the point where you can start making, you can say, oh, I can start making a different decision. I like the ingredient blending applications, and this is a diet problem here, and I'm going to ask you to do an ingredient blending problem as well. Your assignment for this module is a dietary problem. You'll have to read it to see what I'm talking about. We're going to look here at a diet problem. And in this situation, we're not looking at whether or not you're on a diet. We are looking instead at creating a food for, let's say, the Whole Food Nutrition Center. Not Whole Foods, but Whole Food Nutrition Center, where they want a natural cereal out there, and it's got to have some blend of grains going into this, and then that there are certain nutrients that they also want you to have within that cereal: protein, riboflavin, phosphorus, and magnesium, and at least so much within any one 2-ounce serving. And we get that 2-ounce serving right there in this slide. You need to have pounds of grain of A or B or C, and you need a certain amount of A, B, and C within that 2-ounce serving. Now, you're not going to get a full pound of A in a 2-ounce serving, because that'd be 16 ounces into a 2-ounce. So we're looking at percentages here where we do expect to use a certain amount of A, not a full pound of A, versus the problem we just went through where you didn't know if you might be able to break up that unit that we were looking at before. So what you want to do also is minimize the cost per pound. So you need to meet the basic nutritional requirements, get a 2-ounce serving of the cereal, and minimize the cost per pound of the grain combination out there. And this is how we create that. So how much do you get out of each protein, out of each grain of protein, riboflavin, phosphorus, and magnesium, how big, how many ounces have you created overall, and you have to use non-negative numbers in terms of the amount of grain that you use for any one of them. And that's your Excel solver solution right there. And what it says is that you're using 0.025 pounds of grain A, 0.05 of grain B, and 0.05 of grain C. And that your actual cost for this is just over a nickel per serving, based on the costs of 33 cents a pound for A, 47 for B, and 38 for C. And that you have met the protein requirements, you've exceeded the riboflavin requirements, you've met the phosphorus requirements and the magnesium requirements. So you have the basics for the nutrients, you have a 2-ounce serving, you have an affordable price, and if that's not affordable, if a nickel for a 2-ounce serving is not affordable for this company, then they might have to rethink the suppliers of the grain or the nutrients, etc., what they were doing. Other LP linear programming applications that are out there, you might have something like American Airlines revenue management. So how many people do you have to have on a plane to make it worth flying? How much, where the seat's going to be placed? And now what you see is weight before you take off. They look at weight so that they're also doing baggage handling out there. So you're managing your revenue by how do you keep within the constraints of what the plane can do, and your fuel costs for increased numbers of people and baggage on a plane. How do you weigh that out with how much people are willing to pay to get onto a plane? And hotel industries do that as well. So the hotel industry figures it needs a certain number of rooms sold every night, and how much the minimum amount is that they can rent a room out and be able to pay all the bills, make it worth renting the room out given the costs that go into it. And then they can sell the room for varying prices on different websites, and they don't have to sell it at the same price out there, where they can pay websites or tour managers differing amounts to get more people in. Some people, some managers or some customers out there wouldn't buy a night at a hotel at a certain price, either high or low, but they might with other inducements out there. Data development analysis. Now, this is not the Drug Enforcement Administration, DEA, okay? They're trying to find out in this situation if there's not a single objective to optimize, what are the inputs and outputs that you come up, and how to make the system essentially run the most efficiently wherever possible. And then finally, for transportation, shipment, assignment problems, etc., we have certain kinds of algorithms, software that's out there that helps for sending stuff one place to another. So UPS, FedEx, Amazon, and these others that have a lot of things to ship from place to place. Walmart with its own shipping vehicles out there. How to either minimize costs or get goods from one place to another with constraints such as weight or perishability, or has somebody paid extra to get it from one place to another. All these things require much more complex solutions than we're taking a look at here, but which actually are pretty interesting. And if you get into this kind of software mix, by all means, you can make a whole lot of cash. That's the end of this chapter.